In this video, we're going to do a quick recap of the problems relating to equilibrium, simple problems. And in the next, we're going to go over some problems regarding what's called ICE tables for more complex equilibrium problems. So let's recall what an equilibrium means. Equilibrium is where you have a reaction, and the reaction can actually go in two directions, left to right and right to left. And we represent that with a double arrow. And when you've reached equilibrium, what that means is that the left to right, so let's call that A, and the right to left, let's call that B, those reactions are have reached an equal rate. So the rate of the forward reaction is equal to the rate of the reverse reaction. And so you can write an equilibrium expression where you have concentrations, and those concentrations can be used to determine if you're at equilibrium or not. So the equilibrium expression can be written as K, which is an equilibrium constant, is equal to the concentration of your products raised to the powers of their coefficient multiplied by each other over the concentration of the reactants multiplied by each other, and they're each raised to the power of their coefficients in the equation that you see. And we saw that there's essentially three different situations for equilibrium systems. For an equilibrium, you can have a K that's larger than 1, a K that's equal to 1, that's smaller than 1, and a K that's equal to 1. So those are the three different options. When you have a K that's larger than 1, it means that at equilibrium, your product concentration is favored over the reactant concentration. When you have a K that's lower than 1, it means your reactants are favored over the product concentration. And when you have a K that's approximately equal to 1, your reactants and products concentration are equal to each other. So equilibrium does not necessarily mean that your reactants and products are equal. It just means that the rate of one reaction is the same as the rate of the other reaction, So you can have an equilibrium situation where you have more product than reactant, and it's still at equilibrium because your rate of forward and reverse are still the same. It's just that you're going to maintain more product compared to reactant while you're at equilibrium. And this, of course, all happens in an open system. A closed system, sorry. An open system would prevent equilibrium from happening. Equilibrium needs to occur in a closed system. So let's go ahead and do some numerical examples as we saw in previous notes in our introductory videos. Calculate the K for the system given the equilibrium molarities. So you can try it yourself. Since you've done problems like this, you can pause the video, try it yourself, then check if you're on the right track. So in this question, we're given the equilibrium molarities. In other words, the concentration is at equilibrium. And so what we want to do is we want to write a K expression for this system. We have SO2 squared because of that 2 in the front here, multiplied by O2 to the power of 1. We don't have to write the 1, divided by SO3 squared. And so we can now plug in our values. So SO2 is 0.29 squared times O2 is 0.18 over 0.50 for the SO3 squared. And we get, 0.29 squared times 0.18 divided by 0.5 squared. We get approximately 0.060552. No units are needed. We have to do this to 2 sig figs, so that would be approximately 0.061 for our equilibrium constant. This equilibrium constant is less than 1. So what that means is that this would favor the reactants at equilibrium over the products. So this favors the reactants over the products. So another type of question that we have to do is one like this, where we have to determine if our system is at equilibrium or not. In the previous question, we were given equilibrium concentration values. So we knew for sure these were at equilibrium. And then we asked you to calculate the K value at equilibrium. And so we can just plug those in. Here, we're giving you some concentrations and we're not sure if we're at equilibrium. So what we have to do is a test. We have to do what's called the Q test. So we've done questions like this before, so you can pause the video and try it yourself and then check your answers by clicking on play. So Q is the reaction quotient. And essentially, if you find that Q is equal to K, then you are at equilibrium. If it's not equal to K, then you're not at equilibrium. So how do you write a Q expression? Is simply your K expression. But the only reason we're not writing K is because we're not sure if we are at the K point yet. So Q is like our tester K. So we're going to write the Q expression, Cl2 times PCl3 over PCl5. And we're going to plug in our values that were given here to see if the Q is going to be equal to K. So Cl2 is 0.064, PCl3 is 0.070, PCl5 is 0.098. We'll then plug those values into our calculator. Just make sure your equation balanced. Always do that just in case it wasn't given to you balanced, and in this case it is, so we're good. 0.064 times 0.070 divided by 0.098. And we get 0.045714285, or we could say approximately 0.0 to 2 sig figs 46. So we found our Q value and we know our K value. So the Q and K are not equal. Q is not equal to K. Therefore, not at equilibrium. In fact, you can predict which direction the reaction still has to go to reach equilibrium. The reaction's still going both ways. It's just that it's going one way faster than the other, and we can see which way it's going faster. So since our Q, which is 0.046, is larger than our K, which is 0.03, we need to decrease the ratio, right? The ratio in the Q is too high. We basically have too much of the stuff up here. We have too much of the product. So since we have too much of the product, the reaction must proceed in the direction that reduces the product and increases this. So we want this to go down and this to go up, the reactant to go up, because we want to reduce our Q value to go towards 0.03. We want a larger denominator, which is a reactant. So the reaction must proceed to the left, towards the reactants. And so that was an example where we were able to, where we had to determine the, or if a system was at equilibrium using concentrations that we calculated throughout an experiment. We weren't sure if those were equilibrium concentrations or not. So when we are dealing with these type of problems, we need to remember that when we're making an expression for K, we only put gases in solutions. We don't include the unit of our K because they vary so much. And also, we typically will express the equilibrium using concentrations. We could also use pressure for gases, and we'll see that in other situations. But what I need you to understand as well is that because we're using molarity, moles, we're actually able to do some stoichiometry using our K value. And so in the next lesson, what we're going to do is we're going to take a look at more complex equilibrium expression questions where we're not given as much information to solve the problem. And to do these more complex questions, we're going to see how to create and utilize tables called ICE tables. And that'll be coming up in the next video.